Good afternoon, everyone, and welcome to Bird Process Equipment's educational webinar on high purity water systems and piping design. I'm Mark Trigenti, the Director of Design Engineering for Bird Process Equipment, and with me today is Madison Mulqueen. Madison, I want to introduce yourself.
Hello, everyone. My name is Madison, and I am a recent addition to our manufacturing sales team at Bird Process, and I will be co-moderating today.
Thank you, Madison. Today we're going to talk about high purity water systems, and we're going to kind of go through some, kind of basics, kind of talking about, water quality, the basic components of high purity water systems, how they're designed, how the different processes are combined together. Then we're going to review a little bit about piping and loop design, and then we're going to end off talking about a couple of case studies here as well. If anybody has any questions as we go along, it's fairly casual. Please use the question window. We will be answering questions throughout the broadcast, as well as at the end there will be more time for questions. Any questions we do not get to during the broadcast, we will email out the answers to as well. There will be a couple of polls posted throughout this as well. Feel free to chime in if you'd like. They are completely optional, and we will follow up this presentation with just a brief survey. We would love to know any feedback that anyone has for us. So now let's get into high purity water system design. High purity water systems, or RODI systems, they come in a lot of different varieties, and they're used in a lot of different applications, everything from medical, pharmaceutical, semiconductor, research institutes, academia, and really understanding a high purity water system is a fundamental process of understanding what your target water quality is, how much of that water you need to generate, and then all of what your feed water quality is, and then all the different processes that need to be combined to achieve that water quality at that volume that you are requiring. But what I want to kind of open up with is a lot of times there's a lot of different terminology kind of thrown around in the industry. People use the term RODI or RODI system or RO or DI system. And really what you're describing when you say RODI is two distinctly different processes, a reverse osmosis system and then a deionization system, whether that's a chemical deionization or that's continuous or EDI, electrodeionization. And while the two are often used in tandem together, they are two very distinct properties. So it's important when talking about an RODI system, either with a client or in your own facility, what you really want to start with is an understanding of what the various water qualities that you might be trying to achieve are. And one of the most common ones is the ASTM standards, ASTM 1, 2, 3, and 4. And there are subdivisions of these. There is ASTM 1.1, 1.2, etc. And they get a little bit more into detail. Obviously, those types of charts are available for review. But what I want to kind of highlight here is there's a lot of different parameters that go into the overall water quality of the system. So obviously, conductivity and resistivity, which are inverses of each other, is really a measurement of the electrical conductance, or in this case, electrical resistivity of the water. And that's primarily what people are targeting most often when talking about a high purity water system. It's less so important in the pharmaceutical industry, and then very important in things like the semiconductor industry. But there are a lot of other constituents as well. There's pH, there's TOC, total organic carbons, bacteria, endotoxins, various minerals. And some of these things are addressed by the RO, some of them are addressed by the DI, and some of them are addressed by something completely different than that. So obviously, when looking at this, there's a number of other different kinds of processes in addition to just the RO or the RODI system, which is involved in these processes. A little less commonly used one, but still available, is the CAP guidelines. And these are CAP 1, 2, 3. This used to be known as the NCC LS standards, National Committee for Clinical Laboratory Standards. And there is a little more detail than what I'm showing here, but in general, these were very similar to the ASTM standards. They're just obviously have a little bit of different water quality. You do see these very commonly utilized in places like colleges, for example. They tend to show up quite a bit. And then when you move into higher grade waters, this is just one example. We'll look at another one a little bit later, talking about the pharmaceutical industry. These are electronics grade water standards. And this is what you would typically see in a semiconductor application. ASTM, the E1, E1.1, 1.2, 2, 3, and 4. And as you can see, they start somewhat similarly to the ASTM standards. There's a whole bunch of other items that come into play, such as dissolved oxygen and particle counts. And this is when you start getting into obviously much more intricately designed high purity, or what they refer to as ultra pure water systems. And we're going to touch on this a little bit as we go along here as well. And it does follow a lot of the same basic componentry, but as you can see, you can get into some very detailed and obviously very, very specific kinds of water quality, which is why it's very important kind of upfront in any project that you're doing to have a good idea of what that water quality is. In addition to that, what your actual feed water quality is.
So, Mark, I had a question on that. So, how would you determine the water quality requirements for a system? For example, how do you know if it is an ASTM type 1 or type 2? Some of these methods for figuring out these requirements.
Sure, and that's a question that actually comes up quite a bit, Madison. And it can sometimes be difficult, and it can be very easy. If you're working in an application, an industrial or semiconductor application, very often a good place to start looking at things, those items, is if you have particular tools or machines, they'll often have a requirement for what is the best water quality to use in them. So that's a good place to certainly start. Even if you go down to even simpler pieces of equipment, say you're in an academic setting, looking at things like glass washers or autoclaves, they will often also have some kind of water guidelines. It does get a bit tricky beyond that. Very often for research applications, they'll basically design that based on their processes. If you really don't have a good idea of what that is, I say, well, if it's a laboratory or academic setting, it really kind of comes down to what type of a building you're trying to design. If it's more of a healthcare or medical kind of application, you're probably looking a little bit less at the bacteria. You're looking a little less at resistivity and conductivity, and probably reviewing a lot more, and probably looking a lot more at things like bacteria or endotoxins that might push you more to say like an ASTM type 2 system. If it was like a geology or chemistry, maybe more ASTM 3 or ASTM 1. And if you really don't know what you're looking at in those kind of situations, a lot of times people will just run a more middle of the grade system like an ASTM Type 2, and then utilize what's referred to as a local polisher at the various points in the system, and that will then allow you to be able to essentially increase the water quality if you need it for a very specific application. We talked a lot obviously just now about water quality, but really what is actually in an RODI system or high purity water system. Most high purity water systems are broken down between two main parts: the pretreatment and the reverse osmosis portion of the system to a storage tank. This is often referred to as the generation portion of the system. And then everything downstream of the storage tank, where circulation, exchange, UV, filters, additional processes are referred to as the it's referred to as the distribution portion of the system. And what's interesting to note is your pre-treatment portion of your system is actually where majority of the work for creating high purity water is actually done. So when I talk about pre-treatment, everything in the pre-treatment system is designed to allow the RO unit to operate properly. It's taking your city water or your groundwater or whatever your feed water source is in that case and bringing it to a level that would allow your RO to operate properly. And very often that entails softening the water. Obviously, having calcium in there when you get to an RO bed can cause the membranes to foul. Reduction of any kind of suspended solid by basic filtration. Carbon filtration to take out any chlorine that could then oxidize the RO membranes, as well as other things that come into play such as pH, temperature. Those aren't so much an impact on the RO, but they're more of an impact on what the RO efficiency can be in that case. So what is an RO system? An RO system is a semi-permeable membrane to separate and remove dissolved solids, organics, pyrogens. Those things actually cause fever in the human body. Submicron colloidal viruses. Essentially anything below 0.045 micron is considered a dissolved solid. Your RO system is essentially using high pressure to push those particulates against the osmotic gradients. You have a permeate, which is your clean water, and then you have a reject stream, which is the water which is going to have the concentration of the items that you just removed. Typically with osmosis, you move from an area of high concentration to low concentration. In this case, you're going in the opposite direction. The RO system is taking out 95 and 99% of the total dissolved solids. Every item that we're looking at, for the most part, of any water quality is essentially a dissolved solid. So your RO system is really doing 95 and 99% of the work required to get you from your base water quality to the water quality you're trying to achieve. And everything kind of downstream of that is really just that kind of final polishing to basically move that water to a very specific level. So your RO system is actually, by and large, the most important component of any high purity water system in general. So ROs operate at fairly high pressures, and they run from 150 to 300 psi. And designing an RO can kind of be a very simple process or a very complicated process, and that's because it really depends on the flow rate that's involved in it. Every RO system is going to have some form of a reject. So water that you put into it, you're going to get a permeate out, but you're also going to end up with a reject stream. Optimizing the permeate out, as well as optimizing the water quality that you get out of it, is typically done with what's called an RO projection. And I'm going to go through one here in a couple of minutes that kind of shows how you can really go into the design of an RO system to really optimize the water quality as well as the water pressure and constituents that you're trying to remove from your system.
Mark, so I had another question for you regarding RO system. So we see that the pressure rating is very high in these kind of systems, but another thing that's a very real question for a lot of customers looking to design these systems is influent temperature of the water. So what is the impact of maybe a high or extremely low temperature on an RO system design?
That's a good question, Matt. I guess one of the things that you'll see, and anybody who's familiar with them, you'll see a lot of times people will advertise kind of off-the-shelf RO units. And, people do make standard packages of ROs in the relatively small range, say half a gallon a minute to say 10 to 15 gallons per minute. And they're always rated at 70 degrees Fahrenheit. And a lot of people also, I've heard people say, I want to use thermostatic mixing valve, or I actually want to boost the temperature of the water to put it through the RO membrane. And there's kind of pros and cons of doing both of that. One of the things you have to remember is that an RO is ultimately a filter. So if you put water in at a higher temperature, you're actually opening up the porosity of that filter. So in a sense, you're going to get more throughput of water, but you're also going to get more throughput of the suspended solids that you're trying to remove from it. So actually, ROs operate best when they're cooler. Typically, a good operating range for an RO is 50 to 60 degrees water, because at that point you have much tighter porosity of your RO membrane, but you will then have a drop off in your permeate rate in those cases. As a result, what you have to do in that case is you have to increase the pressure basically to compensate for that. So when you see an RO that's rated for 3 GPM at 70 degrees Fahrenheit, if that water is now 50, that RO probably runs at 2.5 or 2.2 GPM. Not a huge difference when you're talking about a smaller RO. You get to 20 or 50 GPM ROs, and now you're talking about a 10 or 15 GPM, difference in flow through it. But you're also now talking about a lot more downstream requirement for treatment in those cases. It's also worth noting that hot water ROs are very sensitive. So if the water gets up to say about 100 degrees Fahrenheit, you do run the risk of actually deforming the RO membranes. They do make high temperature RO membranes. Those are generally only utilized when you have steaming. You have a steam requirement for sanitization for an RO system.
Great. So that's a very significant consideration. Thank you.
Thank you. One of the good rules of thumb is obviously when you have an RO, as we were just talking about temperature, you do have this reject stream, and kind of the generic rule of thumb is, your reject stream is going to be somewhere between 50% for very unoptimized ROs up to about 25%, reject rate, for more well-designed ROs. And one of the things you have to realize is a good way to really measure that is that is really what's called percent reject. So that's two conductivity probes that are basically put across um, the RO membrane that allow for treatment. So what you're looking at there is if you're basically monitoring you're monitoring what the conductivity is coming in versus what's going out. And that gives you a very good measurement overall of what your RO efficiency is in those cases. I do have one question here that just came up, which is can I elaborate a little bit more about what the difference between an RO unit and a pharma RO unit is? And so that kind of gets a little bit into kind of a little bit of a side topic, but I want to just kind of talk about it here for a second. Fundamentally, there can be no difference between the two of them. USP grade water can be made either by an RO or by a distillation process, which is kind of, in a lot of pharmaceutical applications, takes the place of an RO unit. And for the most part, a lot of times those will operate very similar from a lab RO to a pharmaceutical RO. Will be very much the same in both cases. A lot of times the sanitization process starts with the storage tank and doesn't directly impact the pretreatment system of the RO. In some cases, however, what they will do is called hot water sanitization. And this is common when you're, depending on what the pharmaceutical requirements are. And in those cases, they will hot water sanitize not just the RO, but everything upstream, water softeners, multimedia filters, etc. In those cases, the RO membrane is typically a stainless steel. So the RO housing is typically stainless steel instead of fiberglass. And the RO membrane is just designed for that hot water sanitization in those cases. An RO system cannot be fully drainable, but it can be flushed, obviously, to drain, and that's typically what they do when they hot water sanitize those types of systems. As I mentioned earlier, one of the things that's important about an RO, one of the things that kind of gets into a little bit of intricacy about an RO system is what's called the RO projection. And in this case, an RO projection, what you're doing is you're taking that kind of generic rules of thumb, like I put X counts in, I get 75% out. And you're looking at how you're really optimizing that. So this is just one example here, without getting too detailed into it. You're going to have some flow rate in 75 GPM. You have a feed pressure of 230. Then you look at your temperature here, if it's 55 degrees, and what you're developing is what's called different stages. So this is often called an array. And an array of membranes is the feed from one into the first stage, then sends the reject to the second stage, to the third stage, to the fourth, et cetera. And then all those combine to basically form your permeates. And if you kind of look at the different stages or arrays here, you can see this is some of the more common ions which are involved: ammonium, potassium, sodium. You can put in what their initial feed values are, and you can kind of see at the end here where the overall total is. And you can see that you've dropped considerably down in TDS here from 125 all the way down here to like 1 essentially. And that's what's really, not TDS, the TSS. You can see essentially where your overall water quality is with these types of systems. And this is kind of where you get into the engineering of an RO system, because you can vary this. You can vary the membrane area. You can do two membranes, then go to a single membrane. And there is definitely kind of a science behind that as well. We do have one more question here, which kind of talks about two-pass ROs. And what a two-pass RO is you're essentially sending you're basically putting essentially two sets of RO array membranes in series, and you're sending the reject of them essentially back to each other. Two-pass ROs for pharmaceuticals is not inherently required. As a matter of fact, two-pass ROs are typically utilized in semiconductor industries, where you're trying to achieve a very high resistivity in a lot of those cases, because you're trying to get out either some very specific ion content, like a boron or something like that, because what you're doing there is, really any RO can be designed as a two-pass. There's a fair amount of there's definitely additional expense involved in doing a two-pass RO. You will ultimately get a higher water quality out of it, but it isn't so much targeting, say, like a bacteria spec. It's usually designed more to target, designed to target more of an ionic spec in those cases. This is what an RO looks like. You can kind of see here on the right, you have your high pressure feed pump. This is where you have your present reject monitoring in those cases. And this is your array of membranes. You have here you have a 2 by 1 by 1. This is your feed water in. This is your end permeate out. The reject of the first set of arrays goes to the second, goes to the third. This is your final reject. And then all these combine to form your overall permeate in these cases. And even a portion of the end reject is put back in. You actually need to have, I guess, quote unquote, dirty water essentially to come into your RO system to really allow them to actually operate properly. This is just a more elaborate version where you see you have a heat exchanger for cooling. And again, here's kind of the complete PNID of sort of an overall RO system. We've talked a lot about RO systems in general, but now obviously, really the next big one that comes up very often is ion exchange. And ion exchange is very different from RO systems, and ROs are a mechanical filter process. You're basically trying to remove all the dissolved solids in the system, either by going, through a mechanical filtration process. When you're talking about ion exchange either chemically or as an EDI process, we're going to talk about chemically here first. You're essentially exchanging a charged ion for another charged ion. So as you pass this through, you're chemically swapping either a proton or an anion for you're swapping either a cation or an anion for a proton or a hydroxyl to basically form water. So ion exchange can pull out a lot of the same things that an RO can, but really it's designed to kind of focus on the very specific ionic content which will pass through your RO. And this will move you out of the resistivity range, which you typically see off of an RO is about maybe a half a mega ohm or less, up to 5, 10, and even up to 18.3 mega ohm in those cases. The problem with chemical ion exchange is you only have X amount of sites in the system. So as you operate an ion exchange system, you have what's called resin exhaustion in those cases. And with resin exhaustion, you'll then have to regenerate the resin. So you do have a bit of a consumable here. It's one of the reasons why people would want to put an RO upstream of any kind of a DI bed. As in a lot of cases, when you have a DI bed, if you just brought basic city water to it, you would exhaust the resin very quickly. It could be a matter of even a couple of weeks in those cases. At this point, we're going to have our first poll question for those who are interested in it. All right. Obviously, this was just in relation to our RO discussion we just had. Obviously, RO systems are designed to remove total dissolved solids in these cases. Going back to ion exchange, you can see here there's a number of the different ionic content which was involved in the system, which we just talked about: calcium, magnesium. So these are all on the kind of the RO projection. And again, you will take out 99% of these, 95, 99% of these in the RO, what you're really doing with ion exchange is you're taking out that basically balance to a degree, moving these down into sort of the ppb range where you're going to get that much higher resistivity that a lot of high purity water systems require. And ion exchange is typically done through some kind of a resin bottle, the most common size being a 14 by 47 inch, which is 3.5 cubic feet. This treats roughly 10 gallons per minute, so it's kind of a sort of a nice kind of sizing to kind of base it on. That being said, resin exchange bottles do change, depending on sizing. And it's interesting to note, ion exchange bottles, or where resin is put in the system, can really kind of be in a lot of different places. Very often it's in the polishing loop downstream of your system, but very often it's also right after your RO. It's not uncommon to go right from your RO into an ion exchange bed. This is particularly true even though you won't be polishing it through your loop. It's very common just when you don't need quite as high a water quality. Again, if you were targeting, say, something which requires like an ASTM 2 spec, 1 to 2 mega ohm, you don't have to constantly polish your high purity water through a resin bottle. You can very easily just have it flow from the RO through the resin bottles, and then maybe even have a slipstream coming back to it. Kind of one of the more I guess, semi-recent advancements in high purity water systems is electro-deionization. One of the downfalls of just DI in general, or chemical deionization, having resin in the system, is it adds a consumable to the system. And that consumable is, obviously you're going to have to exhaust your resin. So you have multiple bottles in series. It's the first one, exhaust. You swap it with the next one. You put a fresh resin bottle in, etc. Now you either have to exchange it or you have to use chemicals such as hydrochloric acid, etc., to then regenerate it. There's a lot of kind of issues with that. So one of the things that kind of came up in the last 20 years is more electro-deionization. And with electro-deionization, it has no actual resin or chemistry to it. What you're essentially doing is using electricity to essentially pull the ions out of your water. So you have, in this case, you're passing your anions and cations, your calciums, your chlorides, things like that, and using a cathode and an anode, you're pulling the ions out of the water. This is good because you really don't have any kind of actual downtime or chemicals involved, and to some degree, you can kind of control based on sizing and current what your end result ion exchange will be. With a resin bottle, you don't have any kind of control. It's going to flow through it, it's going to exchange, and that's kind of where it's going to develop into. With electro-deionization, you do have that ability to do a little bit of control. It also saves a lot of space. These units can be considerably smaller. The downside of EDI, it takes a lot of power. It takes a lot of electricity to do this. So very often EDI systems will require a separate power feed to your system. But again, it removes any real chemical components from being a part of your high purity water system. It's also fairly common to use these in conjunction with each other. EDI and DI together are often utilized to make ASTM type 1 or higher, like electronic grade water in those cases. We have a question coming in. Is EDI required based on the incoming water quality? No, EDI is not required based on the incoming water quality. EDI is an option to achieve a water quality. Anytime that you have EDI cannot be utilized without having gone through an RO. If you have not really generated RO water in that case, an EDI system will simply not operate properly. You need to get the ionic content to a certain level to be able to utilize EDI. EDI is an option to replace either replace the resin bottles or work in conjunction with the resin bottles. That can go into a system. Another question on the EDI, what is the total power consumption of the EDI system? That depends on the size, to be honest with you, but kind of a ballpark. One, if you had say a 10 GPM EDI, I would probably put a 30 amp 460 volt feed to it. They can operate, again, it's fairly high voltage, relatively speaking, when it comes to an EDI system. So really anything kind of, in that sort of say 5 to 15 GPM range, you're probably looking at about a 30 amp power drop for it. which relative to the rest of the system. That's why very often it's separated into its own power panel in those cases. Kind of moving away from the RO and DI for a second, we did mention earlier that obviously bacteria as well as TOC is also a major component of a lot of high purity water systems. And that's where, TOC and bacteria are removed upstream, obviously, as part of the DI and as the RO. But really, that final polishing is done with what's called UV or ultraviolet lights. And ultraviolet lights work in either the 255 or 185 nanometer UV range. One is the vacuum UV, one's a short UV range. 185 nanometers is essentially designed to target TOC reduction. 254 is designed for disinfection. And when I mean disinfection, you're basically destroying the bacteria. You're not actually removing it from the system. This will cause endotoxin buildup, which we'll talk about here in a second. And the TOC, that's a big component of a lot of things, reducing that down. It is worth noting that the two are not interchangeable. Obviously, you cannot 185 and 254 do not have the same impact. However, 185 nanometer UVs do have a 254 nanometer peak in them, albeit much smaller. So sometimes you can, depending on what your bacteria requirement is, just use a 185 nanometer UV in those cases. But they are oftentimes utilized in conjunction with one another. This does not prevent the need for sanitization having a UV light. This is really affecting the instantaneous water quality of your system in general. It's also worth knowing that 254 nanometer UV can also destroy ozone. So should you have ozone either in your system or as part of a sanitization process for your system or your loop in those cases. We have a question on the UV. Is it recommended to use both 185 and 254 nanometer in a pure water generation or just 254? That depends on what your requirements are. So if you, coming off of your RO, you will probably have a TOC count of 100 to 250. So if you have to get your TOC level down to say 50 for like an ASTM1 type system, then you need a 185 nanometer UV in there. If you have to get it lower than that, then you need, so it really, if TOC is relevant to your water quality, you need a 185 nanometer UV. Almost all of them have a 254 nanometer UV in them for bacteria. And bear in mind that most of the bacteria in your water is actually going to come from your pretreatment system, your RO, your resin up there. So that's where a lot of your bacteria, sometimes 254 nanometer bacteria are actually utilized on the pretreatment side of your system. But yes, that's a water quality question. If you're generating a system that requires anything less than, say, 100 or 200 TOC, you need a 185 nanometer TOC light in the system. And TOC sizing is a little bit different. TOC sizing, because they usually size it either on a single pass or multiple passes through the UV light. So if you have to do a single pass reduction, your flow rate, your sizing for your UV light can also change. So maybe you're operating closer to, say, 2 or 3 times. So for example, if you had a 50 GPM flow, you may need 100 GPM rated 185 nanometer TOC lights in those cases. And then lastly, one of the more common components in the system is obviously the final filter, generally 0.2 to 0.5 or better. And they can obviously go much lower than that, down to 0.03, down to 0.03 in those cases. And really what these are doing is they're taking out endotoxins, any residual from the UVs or the resin, not the resin catch filters, anything residual in your system. And due to the cleanliness of the water, it's very often that that these filters will not be exchanged for probably almost 6 months to a year in those cases. Kind of in between the generation and the in the polishing side of your system, you have your storage tank. And really, this is one of the things that we talked about earlier is For an RO system, you're going to have to know how much water you need to make and how much water you're going to use in your loop, which we're going to talk about here in a second. Your RO or your pretreatment in general generally feeds the storage tank, and this also becomes the point where you will control the pressure of your loop. So as you draw off of the tank, you go through your resins, your filters, your UVs, you're ultimately going to pass back through your loop, and then you're going to come back through your return header here and into your actual storage tank. And this is kind of sized based on what the drawdown rate is of your loop, but also on the makeup rate and your water quality. The higher the water quality, the smaller the tank, because it's very hard to keep a tank like this very clean for an extended period of time, even while you are doing that polishing. The tank is sealed to the air. You have vent filters up here, 0.2 hydrophobic filters to prevent anything from getting drawn into the tank during either the pump down or the vacuum phases of your tank. This is also where your sanitization process typically begins, whether it's chemical sanitization or steam or hot water. Obviously, a plastic tank here, we're talking about chemical. If you're in the pharmaceutical industry, you'd be talking more about stainless steel in those cases.
So, Mark, I know that with those storage tanks, you have obviously the interest to minimize any kind of bacteria growth at all. So we know that these tanks often use nitrogen blanketing. So is that a form of, keeping the bacteria out? What is the main purpose of that?
Really what you're talking about when you have nitrogen blanketing is not a bacteria issue to prevent the atmosphere from getting drawn into the tank. When you're generating water of a certain quality, literally the CO2 of the atmosphere can actually want to get dissolved back into your water, and that can basically allow the resistivity of your water to actually drop in those cases. So you're talking about very high purity, like ASTM1 or above. You very often put a nitrogen blanketing system in there to allow that water quality to be maintained at all times, a very thin layer.
Okay, thank you.
One of the things that kind of came up sort of recently, just as a little bit of a side topic here, is what's referred to as RO, or just high purity water reclaim. Just want to touch on it here for a second. Obviously, with any RO, you do have a reject stream which is involved in it, and on a very small system, say 3 or 5 GPM in those cases, your reject could be 1 or 2 gallons. You start talking about very large systems, say 50, 100 GPM, and you could be operating, you could have 25 or 30 gallons per minute when the RO is in operation of just basically rejected city water in those cases. So there has been a push recently to implement RO reject reclamation. There's something really wrong with the water in general, which is very concentrated city water in those cases. So it can be used for a lot of non-potable things. Certain cities and other green initiatives have kind of pushed in that direction. Not so much in industry, more in academia and healthcare and places like that. But just so everybody's familiar with it, it is kind of an up-and-coming topic, obviously, as more environmental initiatives are kind of brought to the fray. We haven't touched too much on this, but throughout obviously any high purity water system, we go through a case study here in a minute. You're going to see there's a lot of instrumentation involved with these systems, between pressure monitoring on the pumps. We talked about resistivity. You can get TOC monitors as well for this system. And some of the obviously the more instrumentation, sometimes when you get into more validatable systems, can get relatively expensive in those cases, but you can in a lot of ways measure almost any one of the parameters which is involved within a system. Going to kind of switch gears here a little bit to sort of the third part of any high purity water system. So we've talked about the generation, we've talked about the distribution, we've talked about water qualities, but obviously moving from the system to its actual point of use, one of the things that comes up very often is the actual recirculation loop. You've made a very high purity water system, and you obviously need to keep this. You need to keep that water quality maintained from what's delivered from the actual system to its point of uses. And there are a number of different materials which are utilized for plumbing loops, and the loops can vary considerably from very large to very small, as well as multiple levels. And from a material standpoint, you have polypropylene, you have stainless steel. Lower quality or RO-based systems can also have PVC in those cases. PVDF as well can be utilized. PVDF has a couple of advantages in that, one, if you have to ozonate your system quite frequently or sanitize, PVDF is a lot more resistant to ozone. It's also the only plenum rated material outside of stainless steel. This can be utilized for a thermoplastic loop. And in addition, you also have sanitary thermoplastic piping, such as a SIB or beading crevice free. And beyond being a typical butt or socket weld, what you're basically doing is you have a bladder in there which expands, which then allows for very, very smooth, basically butt weld between the joints when you're talking about a sanitary thermoplastic system. And obviously stainless steel, which is always a sanitary system in those cases. And choosing this material is kind of really a choice between obviously the economics of the system. Loops can be very large, 600, 700, 800 feet, and also maintaining the water quality that's also involved with it. If you're in the pharmaceutical industry, you're going to almost exclusively be a stainless steel based system because of the steaming sand, because of the bacteria requirements. Although they do make thermoplastic, they do see thermoplastic sanitary now. Higher education or labs, you're probably going to be polypropylene or PVDF. Semiconductors, generally PVDF and or some form of a sanitary thermoplastic in those cases. And this is kind of how a loop is essentially laid out. This is just one example here. And there are essentially two forms of loops. What's referred to as a serpentine loop and what's referred to as a ladder loop. And a serpentine loop is kind of what you classically think about, where the water essentially leaves your high purity water system and then basically passes through a single line of piping and then comes right back to your system. It's one continuous, essentially, pipe run. And that's very common when you have single floor, relatively small loops. If it's a single lab or say it's an industrial complex, you're just going to go around the building essentially. That's where you typically see a serpentine design loop. Ladder loops tend to be designed more in the case that you have a multi-story building, whereby you basically have a main feeder and a main return loop, and then every level in between essentially has its own individual loop where you're individually controlling the back pressure off of the individual loops, and then you're controlling the main feed pressure back at the actual tank return at that point. Unlike, say, like a hot water system, everything in a high pressure water loop is all balanced based on pressure in the system, not flow. And flow is kind of a tricky thing when it comes to high purity water systems, because what you need to do is you do need to maintain a certain turbulence in the system, not necessarily a certain velocity in the system. So a lot of times when you're talking about these kinds of systems, what you're looking at is having a flow to basically compensate for whatever you take out of it to basically maintain that particular turbulence within your actual system. I think we're going to have our last poll question now. Hopefully we don't disconnect again. All right. Obviously, we just talked about different plumbing materials. The only plenum-rated thermoplastic piping in this case is PVDF. So obviously, going through a high purity water loop design, one of the things I was just talking about is you're looking obviously when you're designing this to maintain a pressure, but you're also making to maintain a turbulence of flow. It isn't so much that a particular flow rate is relevant, a particular velocity is relevant in a lot of cases, but you do really kind of size it really based on, and this is going to depend on the material, whether it's PVC in this case or 316s. You can see different ODs at different velocity. You kind of want to really be kind of in this range, sort of this 4 to 7 feet. Generally speaking, 5 feet per second. But really, what you're looking at here is not so much velocity as it's going to be the turbulence of your system, and that's kind of what we're looking at here is the overall turbulence. So if you have a loop design and you have to maintain it for say you may have an overall usage of say 30 GPM, you might be putting 50 GPM through your loop because even though you might be draining that out, you can't really drain the loop down in those cases. And this also kind of comes back to the storage tank size. You can see polypropylene somewhat similar. And it really depends on what your piping material is and ultimately how you also design the loop in those cases. And obviously the pressure loss across it as well. It is worth noting you do have a pressure loss in your RODI system as well, which can actually be quite a bit. So if you have distribution where you're going to have filters, UVs, DI beds, you could lose 30 pounds just going through the distribution of your system, plus your loop, plus all of your different valving. If you have a system where you may be in excess of 150, at your actual pumps, in excess of say 135 psi, or without being in you may have to put in a secondary pressure system in your system. What I mean by that is, what I mean by that is, if you're flowing, you may need to say as a higher rate, you may need to put a drop off of your loop to another basically booster distribution, kind of polishing system in those cases. That's not very uncommon.
So, Mark, I had a question regarding the loop sanitization itself. So, what's involved in that process, and how often, how do you gauge how often you need loop sanitization to be performed?
So loop sanitization is done a couple of different ways. Really, you're either going to do it by a temperature or by a chemical. And the chemical method is either going to be done with ozone or a peroxide-based solution, and the chemical is either hot water or steam. Kind of regardless of how clean you make your water and how much, and how your loop is designed, over time you are going to get buildup in the actual piping system. So in a lot of ways, it is a function of your water quality, CFUs per mil, of how much you want. Depending on what your CFU per mil count of your water quality is, that depends how often you need to sanitize your system. If you're a pharmaceutical company, you're sanitizing it every day. Semiconductor, possibly every week or two, and then, or somewhat more continuously when you talk about the electronics grade systems. And then in general, laboratories, places like that, depends again on what kind of what the tolerances are of your water quality. Generally, once a quarter to twice a year is a fairly reasonable estimate. If you're talking about just an ASTM, say 3, or one of those types, a more sort of diversified case there. How you do it with chemicals is simply ozone. Is you basically bubble ozone into the storage tank. You shut down the flow through the resin beds, and you really run it overnight through your system. You then turn the UV lights on. You can essentially destroy the ozone to oxygen at that point. If you are doing it with peroxide, it's a very similar scenario. Steam and hot water. Hot water, they typically heat up the storage tank, which is actually full then of high purity hot water, and then they flush it through the system essentially to actually clean it with hot water. It's very common in the pharmaceutical industries.
Okay, so you have a couple different options, and it's case by case usually.
It is a case by case. I want to kind of end off here talking a little bit, just like a quick case study, and then also talk a little about the pharmaceutical. I know we're running a little bit late on time after that issue there. again, when you're talking about um, any kind of water, this is just a highlight. I'm going to talk about semiconductor application here, but this is really any kind of system. What you want to look at, obviously, is what your end water quality requirements are, which you can see here. This is obviously semiconductor grade water, so we have different parameters, we have residual, we have different requirements. You're going to do your RO projection in this case. We basically took those requirements here. Obviously, I showed you this one earlier today, earlier in the presentation as well. 75 GPM, 60 GPM flow. I kind of wanted to really show you guys here is the P and ID. That's really the important thing here. In this case, this is really your pretreatment stream at this point. Very often, if you don't have sufficient water pressure coming into your RODI system, you may need a booster pump. You generally want to have about 70 pounds of pressure, 60 to 70 pounds of pressure to be able to get through water softeners. In this case, we have metabisulfite injection in place of the chloramine. Then you have your multimedia filters, and then multimedia metabisulfite water softeners. Then you have your RO system here. And this really would constitute the entirety of the pretreatment system, where you're doing, again, majority of your work. But you can see everything here is really leading up to the actual RO system in this case. You have your storage tank. This is what the EDI system looks like. The EDI obviously also has a reject stream, so you actually have your UV here. Again, because a lot of your bacteria is actually built up in your pretreatment, so oftentimes you'll actually capture that initially within your system and then go through your EDI module before then going on to the true high purity water tank. This is your ozonization. This is where you do your sanitization of the system. And then this is your final distribution, which really is actually a very small portion of your overall system. You have your UV light, resin, final filters, and then obviously coming back here, you have obviously this is where you have your pressure regulation off of your loop. So a lot of people tend to focus really on this part of the system, but a lot of the work is actually done everything really upstream of your system in those cases. These systems can get pretty big. This is obviously a 60 GPM flow rate. This is your city water break tank. This is your pretreatment module. That's the size of your RO with your EDI. There's your EDI power panel there. Then you have your distribution. This is your DI racks essentially here. I'm talking about the life science industry. Again, this is a little bit of not different, but somewhat similar. You can see now I've got more stainless steel in these cases. Typically, high purity water systems or pharmaceuticals rely on either USP or WIFI water. WIFI water, which is water for injection, is made a very different way than what we've been talking about today. It will be done through distillation, which in and of itself is kind of a different technology. USP is also made that way, but it's also allowed to be made through membrane technology, such as an RO. But you can see in this case, really what your primary focus is, you actually don't even really get into the resistivity range, really at the conductivity range, and you're focusing on bacteria and endotoxins and TOCs in those cases. So it's a very different type of water system in that it's really more focused on just very different parameters than most are in those cases. And we talked a little bit about this before. You'd almost always sanitize pharmaceutical systems on a very, very regular basis, and they're typically validated. And validation is kind of its own topic, but in a sense, what you have to do is you have to basically prove that the system works the way you intend it to. And that's going to be things like spray ball coverage and self-drainage and a lot of other things called IQ, OQ, which obviously have any questions, we can talk about that a lot. Because obviously this is being utilized, in a process that validation becomes very relevant at that point. But from a P&ID standpoint, it's not all that dissimilar in this case. When looking at a lab-based system, as you can see here. We do have one more webinar this year, which will be held on November 10th for custom engineered systems. if anybody would like. The registration for that webinar is open at this time. And now we'll have, if anybody has any time for any additional questions, we'll be online for a few more minutes here. And I want to thank everybody for attending. And again, let me know if you guys have any more questions.
So, Mark, we do have a follow-up question in the chat for us, which is sanitization required for all RODI systems or just pharmaceutical applications?
Typically, it's really required for all of them. It's a large focus of pharmaceutical. So really unless you have basically no bacteria requirement for your water, you should sanitize on some form of regular basis. In the pharmaceutical industry, you obviously need to sanitize on a very, very regular basis. Like I said, it could be every day, it could be every week, but sanitization is kind of an integral part. If it's just the base RO system, such as like a humidifier or something like that, then you would typically maybe not require that in those cases. But yes, 99% of systems will require sanitization. All right, everyone. Any more questions that come in? I think we see a few more. We'll email those. I know it's past 2 o'clock at this point, so if anybody has any more questions, we can certainly address them as they come in. Thank you very much, everyone.